Almost everything around you owes most of its mass to particles called protons. And yet, if you open a proton up and simply add together the masses of the quarks inside it, you find something very strange. Most of the mass is missing, not a little of it, almost all of it. So if the quarks themselves are not providing the weight, then what exactly is? Good evening, and welcome to the Late Lab. I'm very glad you're here. Before we get comfortable, I'd love to know where in the world you're listening from tonight. Maybe you're already tucked into bed, lying on the sofa with the room growing quiet, or listening through headphones somewhere while the rest of the evening slowly fades away. Wherever you are, I hope you're comfortable, relaxed, and ready to let your mind wander for a while. If you enjoy these slower explorations through science, a like and subscribe is always a lovely way to help the Late Lab continue growing. And if you've already subscribed, thank you for coming back. It genuinely means a great deal to have you here again. Tonight we're heading inside one of the most ordinary particles in the universe, only to discover that there is almost nothing ordinary about it. A proton contains quarks. Those quarks receive mass through the Higgs field, but together their fundamental masses account for only a small fraction of the proton we actually measure. The rest comes from something far stranger, from motion, from fields, from confinement, from the ceaseless activity of gluons and quarks interacting through the strong nuclear force. So settle in, let things become a little quieter, and we'll begin with a deceptively simple question. Where does a proton get most of its mass from? A proton is one of the most familiar particles in physics, largely because it is one of the basic ingredients of ordinary matter. Every atomic nucleus contains protons, and the number of protons inside a nucleus determines which chemical element that atom belongs to. Hydrogen has 1 proton, carbon has 6, oxygen has 8, and throughout the visible world, these tiny particles quietly provide a large share of the mass of the matter around us. But when we ask where the mass of a proton actually comes from, something rather surprising happens. A proton has a rest energy of roughly 938 million electron volts. That is the energy associated with its mass, when the proton is not moving as a whole relative to you. At first, it might seem reasonable to assume that this mass must simply come from adding together the masses of the smaller particles inside it. The familiar description of a proton says that it contains 2 up quarks and 1 down quark, so we might imagine placing those 3 quarks on a very tiny set of scales, adding their masses together, and expecting the result to be the mass of the proton. But it is not even close. The fundamental masses of those light quarks add up to only a small fraction of the proton's total mass. The exact values depend on how quark masses are defined and at what energy scale they are discussed, but the broad conclusion is unmistakable. If we simply add together the bare masses associated with 2 up quarks and 1 down quark, we account for only a tiny portion of the roughly 938 million electron volts belonging to the proton. Most of the mass appears to be missing. Fortunately, physics has not misplaced it behind the sofa. The problem comes from the assumption that the mass of a composite object must always equal the sum of the intrinsic masses of its individual ingredients. That assumption works reasonably well in many everyday situations. If you place several ordinary objects inside a box, the mass of the box and its contents is very close to the masses of all those objects added together. But at the level of relativity and quantum physics, mass is more subtle. Albert Einstein showed that mass and energy are deeply connected. Energy is not merely something an object can possess alongside its mass. The total energy contained within a system contributes to the invariant mass of that system. This becomes extremely important inside a proton. The two up quarks and one down quark are not simply sitting quietly next to one another. They are part of a highly energetic quantum system. They interact through the strong interaction described by the theory called quantum chromodynamics. Between and around the quarks exists an intense gluon field, and the proton also contains what physicists describe as a quantum sea involving additional quark and antiquark activity. So the simple picture of three tiny particles inside a little spherical container is useful as a first introduction, but it is nowhere near the complete physical description. A real proton is an interacting quantum state. Its quarks carry energy. Its gluon fields carry energy. The interactions between those fields contribute energy. The continual quantum activity inside the proton contributes to the energy of the complete system. And because energy contributes to mass, all of this matters when we place the proton, so to speak, on the scales. This is why asking what a proton contains is not quite the same question as asking where its mass comes from. If we ask what gives the proton its characteristic quantum numbers, the two up quarks and one down quark are extremely important. They help determine properties such as its electric charge and identify it as a proton rather than another strongly interacting particle. But if we ask why the proton weighs as much as it does, those three quark masses alone are nowhere near enough. The overwhelming majority of the proton's rest energy arises from the dynamics of the strong interaction. The United States Department of Energy describes the interactions of quarks and gluons as being responsible for almost all of the apparent mass of protons and neutrons. That means the missing mass is not hiding inside some undiscovered heavy constituent. There is no secret massive particle sitting quietly between the quarks, waiting for physicists to notice it. Instead, most of the proton's mass emerges from what the quarks and gluon fields are doing. The proton is massive largely because it is an extraordinarily energetic quantum system confined to an extraordinarily small region. And that turns the original question into something much more interesting. The mass of the proton is not simply the weight of its ingredients. It is to a remarkable extent the weight of their energy, their interactions, and the restless quantum dynamics that hold the entire proton together. For a long time, the proton looked as though it might be one of nature's basic, indivisible building blocks. That idea made sense historically. In the early 20th century, physicists were only beginning to discover how atoms were arranged internally, and one of the key figures in that story was Ernest Rutherford. Rutherford's experiments showed that atoms contain tiny, dense nuclei surrounded by much more diffuse regions associated with electrons. He later identified the nucleus of ordinary hydrogen as a fundamental positive constituent of atomic nuclei. That hydrogen nucleus is what we now call the proton. For decades, the proton itself appeared to be elementary. But as experiments became more powerful, that picture began to change. By the 1960s, physicists had discovered a growing collection of strongly interacting particles. Their properties seemed complicated at first, but patterns began to emerge. Murray Gell-Mann and George Swake independently proposed that many of these particles could be understood as combinations of even more fundamental objects called quarks. In the modern description, a proton belongs to a family of particles called baryons. Its valence structure consists of two up quarks and one down quark. That statement is completely correct. It is also very easy to misunderstand. The word valence is doing quite a lot of work. When physicists say that a proton contains two up quarks and one down quark, they are identifying the quark content that determines several of the proton's permanent quantum properties. In particular, those valence quarks help determine its electric charge, its baryon identity, and the fact that it is a proton rather than some other strongly interacting particle. Two up quarks each carry positive electric charge, while the down quark carries a smaller negative charge. Together, their charges add to the proton's familiar single positive elementary charge. But this does not mean that a proton is simply three tiny solid beads sitting inside a microscopic shell. There is no quiet little triangle of quarks waiting patiently inside. A proton is much more active than that. The theory used to describe its internal behavior is quantum chromodynamics, the quantum field theory of the strong interaction. In quantum chromodynamics, quarks interact through gluon fields. Gluons are the particles associated with those fields, and they carry the strong interaction between quarks. At first glance, this might sound a little like electromagnetism. Electrically charged particles interact through the electromagnetic field, whose quantum particle is the photon, so perhaps quarks interact through gluons in much the same way. But there is an important difference. Photons do not themselves carry electric charge. Gluons do carry the kind of charge associated with the strong interaction known as color charge. That means gluons can interact with other gluons. And this changes almost everything. Instead of a few particles exchanging simple messages through an otherwise passive field, the proton contains a strongly interacting network in which quark fields affect gluon fields affect quark fields, and gluons interact among themselves. The result is a highly dynamic quantum system. There are also more quark-related effects present than the simple valence description suggests. The proton's full quantum state includes what physicists often call C-quarks and antiquarks. These do not replace the two up quarks and one down quark that define the proton's valence structure. Instead, they appear as part of the much richer internal quantum behavior generated by the strong interaction. At high energies, experiments reveal this complexity very clearly. When physicists probe a proton with sufficiently energetic particles, they do not see three motionless quarks occupying fixed positions. Instead, they observe distributions of momentum shared among quarks, antiquarks, and gluons. And those distributions depend partly on how closely the proton is being examined. At one resolution, a simplified three-quark description can be extremely useful. At much finer resolution, the proton appears increasingly busy. The gluons become impossible to ignore. C-quarks become important. The internal momentum structure becomes far richer than the familiar textbook sketch of three coloured spheres. This is one of the strange but essential lessons of quantum field theory. What an object contains is not always best understood as a fixed inventory of tiny pieces. The proton is better described as a bound state of interacting quantum fields. Its identity remains stable. A proton does not casually forget that it is a proton halfway through the afternoon. But internally, the state is anything but static. Quark fields are interacting with gluon fields. Gluon fields are interacting with themselves. Momentum and energy are distributed through the entire system. C-quarks and antiquarks participate in the quantum structure. All of this takes place inside a region roughly a femtometer across, around 1/1,000,000 of 1/1000,000,000 of a meter. That tiny size makes the amount of activity involved even more remarkable, and it also begins to explain why simply weighing the three valence quarks was never going to solve the proton mass puzzle. The proton is not three light objects somehow adding up to one unexpectedly heavy object. It is a tightly bound, intensely interacting quantum system. The two up quarks and one down quark tell us what kind of particle we are dealing with, but the full quark and gluon state tells us what that particle actually is. And once the proton is understood in that way, the large amount of energy hidden within such a tiny region begins to look much less mysterious. The proton mass puzzle becomes much easier to understand once we stop thinking of mass as nothing more than the combined weight of smaller pieces. That everyday intuition works surprisingly well for many ordinary objects. If you place 3 stones into a box, then weigh the box, the result is very close to the mass of the empty box, plus the masses of the 3 stones. Nothing especially mysterious happens, but fundamental physics does not require every composite object to behave that way. Albert Einstein's special theory of relativity established a much deeper connection between mass and energy. The familiar idea is often shortened to the statement that mass is a form of energy, but for the proton it helps to be a little more precise. The mass of a complete isolated system is related to the total energy that system possesses when measured in its own centre of momentum frame. That means a proton's mass is not merely a total obtained by listing the rest masses of the quarks inside it. It reflects the energy of the entire proton. This distinction also prevents an easy misunderstanding about motion. Suppose a proton travels through a laboratory at an enormous speed. From the laboratory's point of view, that proton can possess a tremendous amount of kinetic energy. But physicists do not describe the proton as acquiring a new intrinsic rest mass simply because it is moving quickly past an observer. Its invariant mass remains the same. The extra energy belongs to the motion of the proton as a whole relative to the laboratory. Now imagine instead moving alongside that proton so that on average, the complete proton is at rest relative to you. The proton as a whole is no longer racing away. Yet internally, it is certainly not motionless. Its quarks possess momentum. Its gluon fields contain energy. The strong interaction continually contributes to the state of the system. All of this energy is still present even when the proton itself has no overall momentum, and that internal energy contributes to the proton's invariant mass. A larger composite object can help make the basic idea less strange. Imagine a sealed container holding energetic particles bouncing around inside it. If energy is added so that those particles move more vigorously, the total mass of the sealed container increases by a tiny amount. The particles themselves do not need to acquire larger fundamental rest masses. The additional internal energy changes the mass of the complete system. The effect is ordinarily far too small to notice with household scales, but the principle is real. Something similar happens with other forms of stored energy. A compressed spring has slightly more mass than the same spring after it has released its stored energy. A warm object has very slightly more mass than the same object when cooler, because some additional thermal energy resides within it. The proton takes this principle into a far more extreme regime. Its light quarks have very small fundamental masses compared with the proton's total rest energy, but they exist inside a system governed by the strong interaction, where characteristic energies are hundreds of millions of electron volts. So the energy associated with the internal quantum dynamics is not a tiny correction added on top of 3 already heavy constituents. It is the dominant part of the story. There is another useful idea here called binding energy, although it has to be handled carefully. In familiar systems, binding can change the total mass of an object. When 2 objects form a bound state and release energy into their surroundings, the finished bound system can have slightly less mass than the separated ingredients originally possessed. Atomic nuclei provide a clear example. The mass of a stable nucleus is generally smaller than the combined masses of the free protons and neutrons from which it could be assembled, because energy is released when the nucleus forms. But the proton should not be pictured as a tiny classical container in which three quarks simply carry positive kinetic energy while an ordinary negative potential energy neatly holds them together. Quantum chromodynamics is a relativistic quantum field theory. The quark and gluon contributions are deeply interconnected. Fields themselves carry energy and momentum. Gluons interact with one another. The proton is a bound quantum state whose energy cannot be reduced to the mechanics of a few miniature balls attached by invisible springs. Even so, the essential accounting principle remains simple. If energy belongs to the proton when the proton is considered in its own rest frame, that energy can contribute to its invariant mass. This is why a collection of very light elementary quarks can form a much heavier proton. The proton's mass measures the energy of the entire strongly interacting state, not merely the intrinsic masses of its easiest-to-name constituents. And once that is understood, the apparent missing mass begins to look rather different. Nothing is actually missing. The mistake was expecting nearly all of the proton's mass to reside in the fundamental rest masses of its quarks. Instead, much of what we call the proton's mass is the mass associated with energy already present inside the proton itself. The quark masses are part of the total, but the motion, the gluon fields, the interactions, and the full quantum structure of the bound state are part of that total as well. For a proton, those internal contributions are not small details. They are most of the answer. At this point, there is a tempting answer to the proton mass puzzle. Perhaps the Higgs field is responsible. After all, the Higgs field is often introduced as the thing that gives particles mass. That description is not entirely wrong, but it is incomplete enough to become misleading when we talk about protons. The real story is subtler. During the 1960s, physicists were trying to understand how the electromagnetic interaction and the weak nuclear interaction could fit into a single consistent theory. Francois Englert, Robert Brout, and Peter Higgs were among the researchers who developed ideas involving a field that would fill all of space and interact with certain elementary particles. This became part of what is now called the Higgs mechanism. The Higgs field possesses a non-zero value even in what we would ordinarily call empty space. Through electroweak symmetry breaking, interactions with this field allow several elementary particles to behave as though they possess rest mass. For quarks, the relevant connection to the Higgs field occurs through interactions known as Yukawa interactions. The stronger a particular elementary particle couples to the Higgs field, the larger the mass associated with that interaction becomes. The up quark and down quark do interact with the Higgs field. So the Higgs mechanism absolutely matters to the proton. Without it, the fundamental masses of these quarks would not have their familiar values. But those values are surprisingly small. On the conventional particle physics energy scale, an up quark has a mass of only a few million electron volts, while a down quark is also only a few million electron volts. Compare that with the proton. The proton has a rest energy of roughly 938 million electron volts. So even if we take the two up quarks and one down quark associated with the proton's valence structure and add their quoted fundamental masses together, we obtain only a small fraction of the proton's total. The difference is enormous. This is why saying that the Higgs field gives the proton its mass is not really accurate. It gives mass to the elementary quarks that participate in the proton, but most of the mass of the complete proton emerges elsewhere. The distinction became especially important after 2012, when physicists at the European Organisation for Nuclear Research announced the discovery of a new particle associated with the Higgs field. Two enormous experimental collaborations were central to that discovery. One was the Atoroidal Large Hadron Collider Apparatus collaboration, The other was the compact muon solenoid collaboration. Both experiments operated at the Large Hadron Collider and observed evidence for a new boson with properties consistent with the long-predicted Higgs boson. The discovery was a remarkable confirmation of the Higgs mechanism, but it also reinforced the need to be precise about what the mechanism actually explains. The Higgs field is crucial for understanding the fundamental masses of elementary particles, such as quarks and charged leptons. It is not a universal container of all mass in the universe. A proton is not elementary, it is a composite quantum system, and most of its mass is associated with the energy of the strong interaction inside it. There is another subtlety here as well. Even the quoted masses of the up quark and down quark are not quite like the fixed masses of tiny classical marbles. In quantum chromodynamics, the numerical value assigned to a quark mass depends on the energy scale and on the precise mathematical convention used to define it. This happens because quantum fields interact with one another, and the parameters used to describe those fields must be renormalized. As the scale at which the system is examined changes, the effective description of the quark mass changes with it. So when physicists quote an up quark mass or a down quark mass, they are referring to carefully defined renormalized quantities. They are not reporting the result of placing a single isolated quark on an unimaginably tiny weighing scale. In fact, isolated quarks are not observed in nature under ordinary conditions at all. They remain confined within strongly interacting particles such as protons and neutrons. This makes the proton a particularly good example of why the phrase mass comes from the Higgs field needs some qualification. The Higgs field helps determine the elementary masses of the quarks. Those masses are real, measurable through their consequences, and essential to the detailed structure of matter. But they do not explain why a proton has nearly 940 million electron volts of rest energy. Most of that value arises dynamically from quantum chromodynamics. It comes from the strongly interacting state formed by quarks and gluons, from their energy and momentum, and from the way the strong force behaves at the tiny scale of the proton. So there are really two different kinds of mass generation involved. There is Higgs-generated elementary mass, which helps give individual quark fields their fundamental mass parameters. And there is dynamically generated hadron mass, which emerges when those quarks and gluons form a strongly interacting bound state. For the proton, the second contribution dominates overwhelmingly. The Higgs field supplies part of the ingredients. Quantum chromodynamics supplies most of the weight. The point where the proton's mass begins to make sense is the point where quantum chromodynamics takes over. Quantum chromodynamics is the modern quantum field theory of the strong interaction. It describes quarks, gluons, and the way those fields combine to produce strongly interacting particles such as protons and neutrons. The theory emerged during the early 1970s as physicists searched for a deeper explanation of the patterns being uncovered among hadrons. Murray Gell-Mann had already helped establish the quark model, and work by Murray Gell-Mann, Harold Fritsch, Heinrich Leutwiler, and others helped develop the colour-based description that became quantum chromodynamics. The word chromodynamics comes from the idea of colour charge. This colour has nothing to do with visible colour. Quarks are not literally red, green, or blue in the ordinary sense. Those names are simply convenient labels for three varieties of the charge involved in the strong interaction. A quark can carry one of these colour charges, and the rules governing how those charges combine are built into quantum chromodynamics. A proton, as a complete physical object, is colour neutral. That does not mean its quarks have no colour charge, It means the colour structure of the entire proton combines into a state with no net colour charge visible from the outside. This is somewhat analogous to an electrically neutral atom containing both positive and negative electrical charges, although the mathematics and behaviour of colour charge are considerably more complicated. The reason for that complexity lies partly in the gluons. Gluons are the quantum particles associated with the field carrying the strong interaction. A useful first comparison is with electromagnetism. In quantum electrodynamics, electrically charged particles interact through the electromagnetic field, and photons are the quantum particles associated with that field. But photons do not themselves carry electric charge. A photon therefore does not ordinarily interact directly with another photon in the same basic way that an electron interacts electromagnetically with another charged particle. Gluons are different. Gluons themselves carry colour information. Because of that, gluons interact not only with quarks, but also directly with other gluons. That single difference has enormous consequences. The field responsible for transmitting the interaction is itself strongly involved in the interaction. Instead of imagining three quarks connected by three neat invisible strings, it is better to picture a deeply interconnected quantum state in which quark fields and gluon fields continually influence one another. Even that picture is only an approximation, because quantum chromodynamics is not fundamentally a mechanical theory of little objects tugging on one another. It is a quantum field theory. Its behaviour is governed by what physicists call a non-abelian gauge symmetry. The term may sound rather formidable, but its important physical consequence here is fairly simple. The charges carried by the strong interaction have a richer mathematical structure than ordinary electric charge, and the force-carrying gluon fields interact with themselves. That self-interaction is one of the central reasons the inside of a proton behaves so differently from almost anything in everyday experience. It is also one of the reasons the proton contains so much energy. The strong interaction does not merely keep three pre-existing massive quarks sitting in a small region. It creates a highly energetic bound state. Inside that state, quarks possess momentum. Gluon fields store and transfer energy. Gluons interact with quarks and with other gluons. Additional quark and antiquark contributions appear as part of the full quantum structure. All of this takes place across a region roughly a femtometer in size. A femtometer is about 1/4 of a meter. Packing such powerful quantum dynamics into such an extraordinarily small region produces an energy scale far larger than the bare masses of the up and down quarks alone would suggest. And because internal energy contributes to invariant mass, this becomes directly relevant to the proton mass puzzle. The strong interaction behaves in another unusual way as well. At extremely short distances, quarks can behave as though they interact relatively weakly. At distances comparable with the size of a proton, however, the interaction becomes strong. This strange behaviour is built into quantum chromodynamics itself. So the proton exists in a regime where the dynamics of the field cannot be treated as a small correction added to three nearly independent quarks. The interaction is central to the object. Remove the quantum chromodynamic dynamics, and what remains is not simply a slightly lighter proton. The proton as we know it would no longer exist as the same bound state. That is why the origin of proton mass cannot be understood by concentrating only on the fundamental masses of the quarks. Those masses matter, but they are small parameters inside a much more energetic system. The proton's roughly 938 million electron volts of rest energy emerge from the complete strongly interacting state described by quantum chromodynamics. This includes the energy and momentum associated with quarks, the energy stored in gluon fields, and the complicated interaction energy connecting all of those components. It is tempting to ask which individual gluon or which particular interaction carries a certain portion of the proton's mass, but that question already begins to force a quantum field system into a classical bookkeeping scheme that does not fit it very well. The proton's mass belongs to the complete state. Its constituents and fields are not independent pieces whose contributions can always be separated cleanly. And this is the deeper shift that quantum chromodynamics introduces. The important question is no longer simply how massive the ingredients are. It is how much energy exists in the quantum state created when those ingredients interact through the strong force. Once the problem is framed in that way, the proton stops looking like an impossibly heavy object made from impossibly light parts. Its mass becomes a consequence of the field dynamics themselves. The same theory that binds the proton together also generates the energetic environment responsible for most of its mass. In other words, quantum chromodynamics is not merely the glue holding a proton together. It is a large part of the reason the proton weighs anything close to what it does. Calling gluons the glue that holds quarks together is a useful first picture. It is also a little too simple. The name itself encourages the idea. Gluons sound as though they must be tiny packets of glue, quietly sticking quarks together inside the proton. But in quantum chromodynamics, a gluon is not a microscopic adhesive. It is an excitation of the gauge field associated with the strong interaction. That distinction matters because the gluon field is not merely connecting otherwise independent quarks. It is an active part of the proton. Gluons carry energy, they carry momentum, they interact with quarks, and, unusually for force-carrying particles, they also interact with one another. This behavior comes from color charge. Quarks possess three possible color labels conventionally called red, green, and blue. Again, these names have nothing to do with visible colors. They are simply labels used to describe different states of strong interaction charge. The gluons have an even richer color structure. Quantum chromodynamics contains 8 independent gluon states. It might seem at first that there should be 9 possible combinations if 3 colors can be paired with 3 corresponding anticolors. But the mathematics of the theory removes one particular color neutral combination from the set of interacting gluon states, leaving 8 independent possibilities. These 8 gluon states form the carriers of the strong interaction, and because each gluon carries a combination of color and anticolor information, gluons respond to the very force they transmit. That makes them very different from photons. A photon carries electromagnetic energy, but it has no electric charge of its own. A gluon, by contrast, carries strong interaction charge. So while photons usually pass through one another without directly interacting in the simplest electromagnetic description, gluons readily affect other gluons. The result is a field that can interact with itself. Inside a proton, this produces an extraordinarily complicated and energetic environment. There is another feature of gluons that makes the proton mass story even more interesting. As elementary particles, gluons are massless. In the standard model of particle physics, they possess no intrinsic rest mass. At first that can sound rather awkward. If gluons have no rest mass, how can a proton filled with gluon activity end up being so massive? The answer returns to the distinction between the rest mass of an individual constituent and the invariant mass of an entire system. A massless particle can still carry energy and momentum. Light provides the most familiar example. Photons have no rest mass, yet sunlight carries energy. Photons can transfer momentum to matter. Radiation can heat an object or exert pressure on a surface. Massless does not mean energyless. The same broad principle applies to gluons, although the strong interaction makes their behavior vastly more complicated. A proton can contain an energetic gluon field even though individual gluons are fundamentally massless. That energy contributes to the total rest frame energy of the proton, and therefore it contributes to the proton's invariant mass. So there is no contradiction in saying that massless ingredients can help produce a massive composite object. The mass belongs to the entire quantum state. The gluon field also plays a central role in one of the most distinctive features of the strong interaction. Because gluons interact with one another, the equations describing the strong force are non-linear. The field does not simply spread outward and weaken in the straightforward way we might expect from everyday forces. At the scale of a proton, gluon self-interactions help produce the complicated behavior associated with confinement. Quarks and gluons remain bound inside color-neutral objects rather than appearing as freely isolated particles under ordinary conditions. The same dynamics also help establish the characteristic energy scale of strongly interacting particles such as protons and neutrons. That scale is enormously larger than the fundamental masses of the up and down quarks. So the gluon field is involved not merely in keeping the proton together, but in creating the energetic conditions that make the proton as massive as it is. High-energy experiments reveal just how important gluons become when the proton is examined at fine resolution. Physicists often describe the internal structure of a rapidly moving proton using Proton distributions. These distributions describe how the proton's momentum is shared among quarks, antiquarks and gluons. At sufficiently high energies, gluons carry a substantial portion of that momentum. And when protons collide at enormous energies, as they do inside the Large Hadron Collider at the European Organization for Nuclear Research, many of the underlying interactions are actually collisions involving gluons or quarks contained within the incoming protons. The proton may arrive at the accelerator as one particle, but at high resolution, its internal gluon structure becomes impossible to ignore. This sometimes leads to the statement that most of a proton's mass comes from gluons. There is truth behind that phrase, but it needs care. The proton's total mass can be divided mathematically in several useful ways, involving quark energy, gluon energy, explicit quark masses and quantum effects, connected to the strong interaction. Those separate contributions can depend on the theoretical framework, energy scale and renormalization convention used to define them. There is no single universal picture in which a fixed percentage of the proton's mass sits permanently inside one particular set of gluons. The safer conclusion is broader. Most of the proton's mass arises from quantum chromodynamic dynamics, and the gluon field is absolutely central to those dynamics. Gluons are therefore much more than the glue between quarks. They are part of an active, self-interacting quantum field whose energy helps create the proton as a massive object. They do not simply hold the proton together, they help make its mass possible. One of the strangest features of the proton is that its quarks cannot simply wander away. If we imagine ordinary objects held together by a force, our instinct tells us that pulling them far enough apart should eventually separate them. Stretch a spring, break a bond, overcome gravity, and sooner or later the pieces come free. The strong interaction does not behave that way. Quarks and gluons are subject to a phenomenon called confinement. Confinement means that isolated quarks and gluons are not observed as freely propagating particles under ordinary conditions. Instead, they appear bound inside color-neutral composite particles known as hadrons. Protons are hadrons. Neutrons are hadrons. So are many other particles built from quarks, but despite decades of extremely energetic experiments, physicists have never simply pulled a single quark out of a proton and watched it travel independently through a detector. The reason is tied to the unusual behavior of the color field. Imagine, very loosely, trying to separate two strongly interacting constituents. With something like gravity or electromagnetism, increasing the distance usually weakens the interaction. The farther two electrically charged particles move apart, the weaker the electromagnetic force between them becomes. The strong interaction behaves differently in the regime relevant to quarks inside hadrons. As color-charged constituents are separated, the energy associated with the color field becomes increasingly important. A common simplified picture describes the field as forming something resembling a narrow tube of concentrated energy between the separating quarks. The farther the quarks are pulled apart, the more energy is stored in that configuration. Eventually, enough energy may be supplied that the system can create new quark and antiquark contributions. Instead of producing one beautifully isolated quark, nature tends to reorganize the available energy into new color-neutral hadrons. So attempting to tear a quark completely free can lead to the creation of additional particles rather than the liberation of a naked color charge. It is almost as though the harder we pull, the more material the strong interaction finds with which to rebuild its prison. This is only an analogy, but it captures the essential surprise. Quarks do not behave like tiny beads trapped inside a box that can simply be opened. Their confinement is part of the quantum dynamics of the color field itself, and this behavior changes depending on the distance scale involved. At extremely short distances, something almost opposite happens. During the early 1970s, David Gross, Frank Wilczek and Hugh David Politzer discovered a remarkable property of quantum chromodynamics known as asymptotic freedom. Asymptotic freedom means that the effective strong interaction becomes weaker when quarks are examined at very short distances, corresponding to very high energies. Under those conditions, quarks can behave approximately as though they are relatively weakly interacting. This was a crucial discovery because it helped explain why high-energy scattering experiments could sometimes reveal quark-like constituents behaving almost like independent particles inside a proton. At larger distances, however, around the scale of a proton, the effective strong interaction becomes much stronger. So asymptotic freedom and confinement are not opposing theories. They are two regimes of the same theory. Quantum chromodynamics predicts that the interaction changes strength depending on the scale at which it is examined. At very high energies and extremely short distances, the coupling becomes weak enough that physicists can often use perturbative methods. These are calculation techniques that treat the interaction as a series of increasingly small corrections. At the scale of the proton, that convenient approach begins to fail. The interaction is simply too strong. This is what physicists mean when they describe the proton as belonging to the non-perturbative regime of quantum chromodynamics. The proton has a characteristic size of roughly a femtometer. That is about 1/4,000,000th of a meter. At distances around this scale, quarks and gluons are deeply entangled in strong non-linear field dynamics. Their behavior cannot be approximated as a few nearly independent particles exchanging occasional gluons. The field itself becomes central. This matters enormously for the proton's mass. The quarks that define the proton's valence structure have relatively small fundamental masses. Yet maintaining those quarks and gluon fields in a confined state involves a large amount of energy. There is energy associated with their momentum. There is energy in the gluon fields. There is energy in the interactions. And because this entire strongly bound system exists even when the proton as a whole is at rest, That internal energy contributes to the proton's invariant mass. This is one reason the proton can possess a rest energy of nearly 1 billion electron volts, while its light valence quarks contribute only a small fraction through their fundamental masses. The rest is not supplied by some hidden heavy ingredient. Much of it emerges from the strongly interacting quantum state itself. Confinement is therefore more than an explanation for why isolated quarks are missing from particle detectors. It is part of the deeper reason a proton has the mass that it does. The proton is not massive despite the strong interaction. It is massive largely because of the energetic quantum world created by that interaction. Very light quarks become part of a far heavier composite object because quantum chromodynamics does not merely place them together. It traps them inside a highly energetic, self-interacting field structure. And that energy becomes part of what we measure as the mass of the proton. Inside a proton, nothing is sitting still. The familiar image of 2 up quarks and 1 down quark arranged neatly inside a tiny sphere can be useful for remembering the proton's valence structure, but it gives a very misleading impression of what the interior is actually like. A proton is a relativistic quantum system. Its quarks do not occupy fixed positions, and they do not follow tidy little paths that could be drawn like miniature planetary orbits. Instead, they are described by quantum fields and probability amplitudes, embedded within an intensely interacting gluon field and confined to a region roughly a femtometer across. That extreme confinement has consequences. Werner Heisenberg's uncertainty principle tells us that position and momentum cannot both be specified with unlimited precision. In simple terms, the more tightly a quantum object is localized in space, the larger the range of possible momenta associated with its state becomes. A proton is extraordinarily small. A femtometer is about 1/4,000,000th of a meter. Trying to confine light quarks to a region on that scale means that their momentum uncertainties become enormous compared with what we are used to in everyday life. This gives us an intuitive reason why the quarks inside a proton are highly energetic. The up quark and down quark have small fundamental masses, only a few million electron volts each in the usual particle physics description. But the characteristic momenta associated with the strongly interacting environment inside the proton are much larger. That means the quarks behave relativistically. Their energy is not dominated by their bare rest masses. Instead, large contributions come from momentum and interaction with the surrounding gluon field. So even though the quarks themselves are fundamentally light, the state they participate in is anything but low energy. This is one of the easiest places to see why the proton mass cannot be understood by simply adding up constituent rest masses. The quarks are carrying substantial momentum. The gluons are carrying substantial momentum. The fields are constantly interacting. And all of that energy belongs to the proton. Gluons make the picture even more interesting because they have no elementary rest mass at all. Yet massless does not mean energyless. A gluon can carry both energy and momentum, just as a photon can. The difference is that gluons also participate directly in the strong interaction with one another, so the proton contains a highly active gluon field whose energy is continually redistributed throughout the system. There is no single moment when the quarks stop moving and the gluon field politely settles down so that everything can be weighed separately. The complete quantum state is the object being measured. High-energy experiments give physicists another way to describe this internal activity. When a proton is accelerated to extremely high speed and then probed with sufficient resolution, researchers often describe its internal structure in terms of partons. The word parton was introduced as a useful way of talking about the constituents seen inside a rapidly moving proton. In the modern quantum chromodynamic picture, those partons are identified with quarks, antiquarks and gluons. Each parton can be thought of as carrying some fraction of the proton's total longitudinal momentum in that high-energy frame. Physicists describe these distributions using what are called parton distribution functions. These do not tell us that the proton contains a permanently fixed set of little objects, each assigned an unchanging slice of momentum. Instead, they describe probabilities for how momentum is distributed among quarks, antiquarks and gluons when the proton is examined at a particular energy scale. And the picture changes with resolution. At one scale, a certain distribution of quarks and gluons is useful. At a higher scale, additional gluon radiation and quark contributions become important. The proton appears richer and more complicated the more closely it is examined. This does not mean that new permanent pieces were hiding there all along in the classical sense. It reflects the quantum field nature of the system. There is also an important distinction between saying that the constituents possess kinetic energy and saying that the proton's mass is simply the sum of those kinetic energies. That would be too crude. The proton's invariant mass belongs to the complete interacting state. The quark momenta, gluon fields, interaction energy, and quantum structure are all tied together. There is no clean classical procedure in which we measure 3 quark speeds, convert those speeds into kinetic energies, add them together, and recover the proton mass. Quarks inside a proton are not independent particles moving freely in empty space. They are confined components of a strongly coupled quantum field system. Still, the underlying idea remains very useful. A tremendous amount of energy exists inside a region only about a femtometer across. The proton may appear quiet and stable from the outside, but internally it is a remarkably energetic object. Its light quarks carry large momenta. Its massless gluons carry energy and momentum. Its fields interact continuously through the strong interaction. And because all of this energy is present even when the proton as a whole is at rest, it contributes to the proton's invariant mass. This is why the proton can be so much heavier than the bare masses of its valence quarks suggest. The mass is not hiding in 3 unexpectedly heavy ingredients. It is emerging from the energy of an intensely confined quantum system. The proton is tiny. But in terms of internal motion, field activity, and strong interaction energy, it is anything but quiet. The proton becomes stranger still when we move beyond the familiar picture of 2 up quarks and 1 down quark. Those 3 valence quarks remain essential. They determine the proton's basic flavor structure and help establish properties such as its positive electric charge. But they are not the complete list of everything participating in the proton's quantum state. Surrounding that valence structure is what physicists call the quark sea. The name is quite appropriate because the interior of a proton is not a quiet place. The gluon field is active throughout it, and quantum chromodynamics allows processes involving additional quarks and antiquarks to contribute to the complete state. So when the proton is examined at sufficiently high resolution, its interior contains far more than 3 simple quark contributions. There are additional up quarks and up antiquarks. There are down quarks and down antiquarks. There are also contributions involving strange quarks and strange antiquarks. At sufficiently high energy scales, heavier quark flavors can participate in the theoretical description as well. These additional contributions are collectively described as C-quarks. One popular way of visualizing this is to imagine gluons continually producing quark and antiquark pairs, which then disappear again almost immediately. You may sometimes hear this described as particles popping into and out of existence. It is a memorable picture, but it should not be taken too literally. Quantum field theory does not really describe the inside of a proton as a tiny room in which perfectly formed particles repeatedly appear from nowhere, wander around for a moment, and then vanish. That image can be useful as a rough intuition for certain calculations, particularly when physicists talk informally about virtual particles, but the deeper description is given by interacting quantum fields. C-quarks are reflected in quantum correlations, scattering amplitudes and experimentally measured Proton distributions. Those are much more precise concepts than a microscopic animation of particles constantly being born and destroyed. The difference matters because the proton does not contain a fixed number of C-quarks in the same straightforward sense that a box might contain a fixed number of marbles. The way physicists describe the quark and gluon content depends partly on the energy scale and resolution of the experiment. Probe the proton one way, and a relatively simple description may be enough. Probe it at much higher resolution, and the structure becomes considerably richer. More gluon activity becomes relevant, more quark and antiquark contributions become visible in the theoretical description. The proton seems to acquire an increasingly crowded interior, although what is really changing is the level of detail with which its quantum fields are being resolved. This C has measurable consequences. In high-energy scattering experiments, physicists can determine how the momentum of a rapidly moving proton is distributed among different types of partons. Those distributions show that momentum is carried not only by the valence quarks, but also by C-quarks, antiquarks and gluons. The C therefore influences how a proton responds when struck by an energetic probe. It affects scattering probabilities, it affects momentum distributions, it contributes to the detailed internal structure revealed by particle collisions. And yet, despite all this activity, the proton remains a proton. The presence of C-quarks does not change its net baryon number, nor does it erase the familiar statement that the proton has a valence structure corresponding to 2 up quarks and 1 down quark. Additional quarks in the C are accompanied by antiquark contributions in such a way that they do not simply alter the proton's permanent flavor identity. This is why the distinction between valence quarks and C-quarks is so useful. The valence structure tells us something enduring about what kind of hadron we are looking at. The C describes part of the much richer quantum activity occurring within that hadron, and once again the proton mass puzzle becomes less compatible with the idea of weighing individual pieces. If the number and interpretation of the proton's partons depend upon the resolution at which we examine it, then asking how much mass belongs to each tiny particle becomes an increasingly awkward question. There is not a permanently fixed crowd inside the proton, with each participant carrying a little labelled portion of the total mass. Quantum chromodynamics gives us something more fluid. The proton is a complete interacting state involving quark fields, antiquark fields and gluon fields. Its measurable mass belongs to that entire state. The C contributes to the internal energy, momentum and interaction structure, but its role cannot be reduced to adding the rest masses of a certain number of temporary particles. That would simply return us to the same classical picture that created the original mystery. The deeper lesson is that the proton is not a bag of independently weighable ingredients. Its interior is defined by relationships between quantum fields. The valence quarks give the proton its familiar identity. The C enriches its structure. The gluons bind the entire strongly interacting system together, while also participating energetically in it. And all of these contributions belong to one quantum object. From the outside, the proton seems remarkably simple. It carries one positive elementary charge and possesses one very definite mass. But beneath that simplicity lies a restless sea of strongly interacting quantum fields. And the more closely we look, the less the proton resembles three particles sitting inside something, and the more it resembles what quantum chromodynamics says it truly is: a single, extraordinarily energetic quantum state. There is another reason the light quarks inside a proton cannot be understood as tiny particles carrying one simple fixed mass. The environment around them matters enormously. Physicists often distinguish between what is called a current quark mass and the effective mass-like behavior that appears when a quark is immersed in the strongly interacting world of quantum chromodynamics. These are not two different kinds of quark. They are two ways of describing the same underlying quark field in very different physical regimes. The current masses of the up and down quarks are small. They are the fundamental mass parameters connected to the Higgs field and used in the Standard Model. But at the low energies typical of protons and other hadrons, quarks interact so strongly with the surrounding quantum chromodynamic fields that their behavior becomes dramatically altered. Physicists often describe such a quark as being dressed. The word dressed does not mean that something literal has been wrapped around the quark. It means that the quark cannot realistically be treated as though it were isolated from all of the interactions surrounding it. Its quantum state is continually influenced by gluons and by the full strongly interacting environment. As a result, the effective behavior of the quark can look as though it carries a much larger mass scale than its tiny fundamental current mass would suggest. This is closely related to a phenomenon called dynamical chiral symmetry breaking. Chiral symmetry is an approximate symmetry that becomes especially useful when thinking about very light quarks. If the up and down quarks were exactly massless, the equations of quantum chromodynamics would possess a stronger version of this symmetry. But the low-energy state of the theory does not display that symmetry in the simple way the underlying equations might suggest. The symmetry is dynamically broken. An important historical figure in understanding this kind of physics was Yuichiro Nambu. His work on spontaneous symmetry breaking showed how the laws describing a system can possess a symmetry even when the lowest energy state of that system does not display it in the same obvious form. That idea became enormously influential across particle physics. In quantum chromodynamics, the strong interaction produces a rich vacuum structure and low-energy behavior in which light quarks become strongly dressed by their interactions. This dressing generates an effective mass scale far larger than the current masses of the up and down quarks. Older and simplified models of hadrons often use what are called constituent quark masses. In those models, an up or down constituent quark may be assigned an effective mass of several 100 million electron volts. That number is much larger than the few million electron volts associated with the fundamental current mass. But it is crucial not to confuse the two. The Higgs field is not secretly giving an up quark hundreds of millions of electron volts of additional fundamental rest mass once it enters a proton. The larger constituent mass is an effective description of a quark together with the consequences of its strong interactions. It packages part of the complicated low-energy quantum chromodynamic environment into something that can be handled more simply. This is why constituent quark models can sometimes reproduce broad features of hadrons surprisingly well, even though they are not the deepest description of what is happening. The full theory remains quantum chromodynamics. One of the clearest signs that chiral symmetry plays an important role comes from the pion. Pions are light particles made from quark and antiquark combinations. Their unusually small masses compared with many other hadrons are connected to the approximate chiral symmetry of the light quark sector and the way that symmetry is broken. In the idealized limit where the up and down quark masses become zero, the corresponding pions would behave as massless modes associated with spontaneous symmetry breaking. In the real universe, the up and down quarks are not exactly massless, so the pions acquire small but non-zero masses. This relationship between light quarks, pions and chiral symmetry provides strong evidence that the low-energy strong interaction is generating structure far beyond what is contained in the bare quark masses alone. And that brings us back to the proton. The proton does not become heavy, because each light quark suddenly acquires a hidden permanent mass of several 100 million electron volts. Instead, the strongly interacting quantum environment generates an effective low-energy scale through the collective behavior of quark and gluon fields. The quarks become dressed. Their propagating behavior changes. The vacuum itself is not trivial. Symmetries that appear in the underlying equations are realized differently in the low-energy world. All of this contributes to the emergence of hadronic scales that are far larger than the bare masses of the light quarks. So dynamical mass generation is not a separate trick added on top of the proton. It is another expression of the same deep fact that has been appearing again and again. Most of the proton's mass does not reside in tiny pre-existing weights carried by its constituents. It emerges from the strongly interacting quantum state itself. The light quarks begin with very small fundamental masses. Quantum chromodynamics dresses them in an energetic environment. And from that environment, a much larger mass scale emerges naturally. There is an even deeper version of the proton mass puzzle, hiding underneath everything we have seen so far. If the up and down quarks are treated as approximately massless, then the classical equations of quantum chromodynamics contain no obvious built-in mass scale anywhere close to the mass of a proton. There is no fundamental number sitting in the theory that simply says a proton should weigh roughly 938 million electron volts. And yet, when the theory is treated quantum mechanically, massive protons, neutrons and other hadrons emerge. So the question becomes more profound. How can a theory with almost no obvious mass scale create one? The answer begins with the strength of the strong interaction itself. In many simple descriptions of forces, we might imagine that an interaction has one fixed strength. Quantum chromodynamics does not behave that way. The effective strength of the strong interaction changes depending on the energy scale at which it is examined. This is known as the running of the strong coupling. At extremely high energies, corresponding to very short distances, the interaction becomes weaker. At lower energies and larger distances, around the scale of protons and other hadrons, it becomes much stronger. This changing strength is not an optional correction added on top of the theory. It is a consequence of the quantum behavior of the quark and gluon fields themselves. David Gross, Frank Wilczek and Hugh David Politzer revealed the high-energy side of this behavior through the discovery of asymptotic freedom. Their work showed that quarks behave increasingly like weakly interacting particles when probed at shorter and shorter distances. That result was crucial for establishing quantum chromodynamics as the correct theory of the strong interaction. But asymptotic freedom also tells us something deeper about scale. The strong coupling is dimensionless. By itself, a dimensionless number does not tell us whether the relevant physics should occur at 1 electron volt, 1 million electron volts, or 1 billion electron volts. There appears to be no ruler built into the classical theory. Quantum physics changes that. As the interaction is renormalized, the coupling begins to depend on energy scale. Instead of being described by one constant number everywhere, its value runs. That running allows the theory to generate a characteristic physical scale, even though the original coupling itself carried no units of mass or energy. This phenomenon is called dimensional transmutation. The name sounds rather dramatic, but the basic idea is elegant. A theory that begins with a dimensionless interaction strength can, through quantum effects, trade that parameter for a characteristic energy scale. In quantum chromodynamics, this emergent scale is commonly associated with the scale at which the strong interaction stops being weak and becomes genuinely strong. Depending on the precise definition, convention and renormalization scheme being used, this characteristic scale lies in the broad range of hundreds of millions of electron volts. That should immediately sound familiar. It is the same general energy territory occupied by hadrons. The proton itself has a rest energy of roughly 938 million electron volts, so the theory does not need to contain a hidden constituent with a fundamental mass of nearly 1 billion electron volts. Instead, quantum chromodynamics generates a strong interaction scale dynamically. And once that scale exists, strongly bound states such as protons naturally acquire masses of the same broad order. This is one of the most striking examples of emergence in modern physics. The proton mass is not simply written into the theory as the mass of one enormous internal particle. It appears because the quantum version of the strong interaction develops its own physical scale. The behavior of the gluon field is central to this. Because gluons interact with one another, quantum chromodynamics is capable of producing the nonlinear running that ultimately connects short-distance freedom with strong low-energy dynamics. At very high energies, calculations can often treat the interaction as relatively weak. Move downward toward the energy scale of a proton, and that approximation gradually stops working. The fields become strongly coupled. Confinement appears. Dynamical chiral symmetry breaking becomes important. Hadronic bound states form. And a world that began with extremely light quarks develops particles hundreds of millions of electron volts heavier than those bare masses alone would suggest. This does not mean that the fundamental quark masses are irrelevant. They still influence the detailed masses of real hadrons and help determine differences between otherwise similar particles. But they are not the main source of the proton scale. The dominant scale comes from the quantum dynamics of the strong interaction. There is an especially subtle consequence hidden inside this story. If the classical equations possess no obvious intrinsic mass scale when the light quark masses are neglected, then they also possess a form of scale symmetry. Very roughly, the equations do not initially single out one particular length or energy as special. But once the theory is quantized and renormalized, that scale symmetry no longer survives in its original form. A physical energy scale appears. This failure of the classical symmetry to survive quantization is closely connected to what physicists call the trace anomaly. The word anomaly here does not mean that quantum chromodynamics has gone wrong. Quite the opposite. It describes a genuinely quantum effect in which a symmetry present in the classical equations is altered by the process of quantization. And that quantum effect reaches all the way to the existence of massive hadrons. The proton therefore gets its characteristic scale from something much deeper than the masses of 3 light quarks. Quantum chromodynamics creates its own scale through the running of the strong interaction. That scale governs the energetic world of confinement, gluon fields and strongly interacting matter, and from a theory that begins with almost no proton-sized mass built into it at all. A proton weighing nearly 1 billion electron volts emerges. There is a particularly subtle idea hiding inside the proton mass puzzle, and it begins with something that sounds almost too simple. If the up and down quarks were treated as exactly massless, then the classical version of quantum chromodynamics would contain no obvious built-in mass scale comparable to the mass of a proton. There would be no parameter sitting in the equations that simply tells the theory to produce an object with a rest energy of roughly 938 million electron volts. And yet the quantum theory still generates massive hadrons. This is where scale symmetry becomes important. In an idealized version of quantum chromodynamics containing massless quarks, the classical equations possess a form of scale symmetry. Very loosely, this means that the equations themselves do not initially select one particular length or energy scale as fundamentally special. If the theory contains no mass parameter, there is no obvious internal ruler saying that something should naturally be the size of a proton rather than vastly larger or vastly smaller. But nature does produce a proton-sized scale. And the reason is quantum mechanics. Once quantum chromodynamics is quantized, the interactions of quarks and gluons have to be treated through a process called renormalization. Renormalization is not merely a mathematical repair job. It is part of how quantum field theories connect their parameters with physical measurements. One consequence is that the effective strength of the strong interaction depends on the energy scale at which it is examined. The strong coupling runs. At extremely high energies it becomes relatively weak. At lower energies, approaching the regime of hadrons, it becomes much stronger. That scale dependence means the classical scale symmetry does not survive unchanged in the full quantum theory. A scale emerges. The mathematical expression of this breaking is closely related to what physicists call the trace anomaly. To understand the name, it helps to introduce the energy-momentum tensor. The energy-momentum tensor is a mathematical object used throughout field theory to describe quantities such as energy density, momentum flow, pressure, and stress. It contains information about how energy and momentum are distributed through a physical system. The trace of this tensor is formed by combining particular components of it in a specific mathematical way. In the idealized classical version of quantum chromodynamics with massless quarks, the trace has a much simpler structure and reflects the scale symmetry of the theory. But after quantization, something changes. Quantum effects introduce an additional contribution. The trace no longer behaves as the classical symmetry would have suggested. That additional quantum term is the trace anomaly. The word anomaly can sound as though something has gone wrong. It has not. In particle physics, an anomaly often means that a symmetry present in the classical description fails to survive the transition to the quantum theory. The theory itself remains consistent. The symmetry is what changes. In this case, that change is deeply important because it is tied to the emergence of the characteristic scale of quantum chromodynamics. Once the strong interaction develops its own scale through quantum effects, it becomes possible for massive bound states such as protons and neutrons to emerge even if the fundamental masses of the light quarks are taken towards zero. This is one reason the trace anomaly is so often discussed in explanations of proton mass. It provides a direct mathematical connection between quantum effects, the breaking of classical scale symmetry, and the emergence of a hadronic mass scale. But there is a trap here. It is sometimes said that the trace anomaly is where all of the proton's mass comes from. That statement is too simple. The total proton mass is a physical observable. It is fixed. But the way physicists divide that total into separate mathematical contributions is not unique. Different valid decompositions of the proton's energy can organize terms involving quark masses, quark energy, gluon energy, and the trace anomaly in different ways. The numerical size assigned to an individual contribution can depend on the renormalization scheme and on the energy scale used in the calculation. So there is no single universal pie chart in which one permanent slice is labelled trace anomaly and another permanent slice is labelled gluons. The pieces are not independent lumps of substance sitting inside the proton. They are terms in a quantum field theory description. What remains robust is the broader physical conclusion. The dominant mass scale of the proton is generated dynamically by the strong interaction. Quantum chromodynamics takes extremely light quarks and massless gluons and produces a massive, stable bound state. The running of the strong coupling creates a characteristic energy scale. Confinement becomes important. The gluon field becomes strongly self-interacting. Quarks become dynamically dressed. And the classical scale symmetry of the idealized theory is broken by quantum effects. The trace anomaly is one of the clearest mathematical signatures of that transition. This makes the proton an extraordinary example of how quantum physics can create something that was not obviously present in the classical starting point. A nearly scale-free classical theory becomes a quantum theory with a definite physical scale. A set of light quark fields and massless gluon fields produces particles with masses measured in hundreds of millions of electron volts, and a proton weighing nearly 1 billion electron volts emerges without requiring any hidden constituent that was born carrying that amount of mass. The trace anomaly does not replace the rest of the quantum chromodynamic story. It belongs to it. It is part of the deeper explanation for how the strong interaction generates its own scale and, through that scale, makes massive hadrons possible. So when we ask where most of the proton's mass comes from, the safest answer is not one isolated mathematical term. It comes from the full quantum dynamics of the strong interaction. And the trace anomaly reveals one of the most profound ways in which those quantum dynamics turn an almost scale-free theory into a universe containing massive matter. Once physicists accept that most of the proton's mass emerges from quantum chromodynamic dynamics, another question naturally appears. Can that mass be divided into percentages? Could we say that a certain fraction comes from quarks, another fraction from gluons, another from the trace anomaly, and perhaps a small remainder from the fundamental masses supplied through the Higgs field? The answer is yes, but only with an important warning. There are useful ways to divide the proton's mass mathematically. There is not one unique, universal pie chart engraved into nature. A major contribution to this question came from Shandong Ji during the 1990s. Ji developed a framework for connecting the proton's mass to the energy-momentum tensor of quantum chromodynamics and separating the total into several physically meaningful terms. The energy-momentum tensor may sound rather abstract, but its basic purpose is straightforward. In a field theory, it describes how energy and momentum are distributed and transported. It also contains information connected to pressure and stress. For a composite object such as a proton, this makes it a natural mathematical tool for asking where the energy of the entire state resides. And because the proton's rest frame energy determines its invariant mass, studying that energy provides a route into the origin of the proton's mass. G's approach allows the total to be organized into contributions associated with several different pieces of the quantum chromodynamic system. One term is connected to the explicit masses of the quarks. Another involves the energy of the quarks, including their motion and their interactions with the surrounding fields. A further contribution is associated with the gluon field, and another is connected to the quantum trace anomaly. This is already much more sophisticated than simply adding the bare masses of 2 up quarks and 1 down quark. It treats the proton as what it really is: a strongly interacting quantum state. Calculations based on this general framework can produce approximate percentages, and these can be very helpful for developing intuition. For example, one representative lattice quantum chromodynamic calculation published in 2018 found a division in which roughly 1/3 of the proton's mass was associated with quark energy. A little more than 1/3 was associated with gluon field energy. Around 1/4 appeared in the contribution connected with the trace anomaly, and less than 1/10 came from scalar quark mass terms involving the light and strange quarks. At first glance, this seems wonderfully tidy. We could draw 4 slices of a circle, label them, and perhaps feel that the proton mass puzzle has finally been organized into a respectable chart. Unfortunately, quantum field theory has a habit of making respectable charts slightly nervous. Those percentages are meaningful within the particular decomposition, renormalization prescription, and energy scale used in the calculation. They should not be interpreted as 4 physically separate substances permanently occupying different regions inside the proton. There is no small patch of the proton containing exactly 1/3 of its mass in quark energy, next to another patch reserved exclusively for gluons. The separate terms are parts of a mathematical description of one interacting quantum state, and some of those terms can change when physicists change the scale or convention used to describe them. This is especially important for the distinction between quark and gluon contributions. In quantum field theory, renormalization affects the way these quantities are defined. Quark and gluon operators can mix under changes of scale, so the numerical amount assigned to one contribution can shift as the renormalization scale changes, even though the total physical mass of the proton remains exactly the same. That total mass is not ambiguous. A proton has one measurable invariant mass, the bookkeeping used to describe how quantum chromodynamics produces that mass can be organized in more than one legitimate way. This is similar, very loosely, to describing the finances of a complicated organization. The total amount of money may be perfectly definite, while different accounting systems group certain costs under different categories. The analogy should not be pushed too far, but it captures the idea that changing the categories does not change the final total. For the proton, the situation is even more interconnected, because quarks and gluons are interacting quantum fields rather than independent departments with separate bank accounts. This is why simple claims such as most of the proton's mass comes from gluons require some care. Gluons are absolutely central to the strong dynamics that generate the proton's large mass scale. The gluon field carries substantial energy. Its self-interactions are fundamental to quantum chromodynamics, and without the strong gluon dynamics, the proton would not exist as the massive bound state we observe. But saying that a fixed exact percentage of the proton's mass belongs permanently to gluons can be misleading. The answer depends on exactly what quantity is being decomposed, how the terms are defined, and at what renormalization scale the calculation is performed. The same caution applies to the trace anomaly. It is deeply connected to the emergence of the quantum chromodynamic scale, and therefore to hadron mass. But it should not automatically be pictured as one physically isolated chunk of the proton's weight. Different valid decompositions can arrange the same underlying physics in different ways. What does survive all of this mathematical subtlety is the central physical conclusion. The direct contribution from the fundamental masses of the light quarks is small. Most of the proton's mass arises from the energy generated by the strong interaction. Quark motion matters. Gluon field energy matters. The interaction between quark and gluon fields matters. The scale generated by quantum chromodynamics matters. The trace anomaly matters. These are not competing explanations. They are interconnected features of the same theory, and this is why physicists continue to study proton mass decomposition so carefully. The goal is not simply to produce a prettier pie chart. It is to understand how a quantum field theory transforms light quarks and massless gluons into a stable object with a rest energy of roughly 938 million electron volts. The different decompositions provide different windows into that process. Some emphasize the Hamiltonian energy carried by quarks and gluons, others emphasize the trace of the energy-momentum tensor and the role of broken scale symmetry. Each can reveal something useful, provided its definitions are kept clear. So the proton's mass can indeed be divided into percentages, but those percentages are not timeless little labels attached to separate ingredients. They belong to particular theoretical ways of organizing the energy of the proton. The deeper truth is more robust than any one set of numbers. Very little of the proton's mass comes directly from the bare masses of its light quarks. Almost all of it emerges from the strongly interacting quantum dynamics that bind, dress, and energize the entire state. The total mass is simple to measure. Explaining exactly how that total should be divided is where the beautiful complications begin. The proton mass puzzle becomes especially convincing when we realize that physicists can do something far more demanding than describe the strong interaction in words. They can attempt to calculate a proton from the underlying theory itself. The difficulty is that quantum chromodynamics behaves very differently depending on the energy scale being examined. At extremely high energies, the strong interaction becomes relatively weak through asymptotic freedom. In that regime, physicists can often use perturbation theory, treating complicated interactions as a sequence of progressively smaller corrections. At the scale of a proton, however, the strong interaction becomes much stronger. The convenient perturbative approach begins to break down. Quarks are confined. Gluons interact strongly with one another. The quantum fields become so tightly coupled that calculating the properties of a proton directly is extremely difficult. This is where the work of Kenneth Wilson became transformative. Wilson helped develop lattice gauge theory, providing physicists with a practical framework for studying strongly interacting quantum fields numerically. The basic idea is to replace continuous spacetime, for the purposes of the calculation, with a discrete grid. Imagine spacetime divided into an enormous collection of closely spaced points. Quark fields are represented on this lattice, while the gauge fields associated with gluons are encoded through connections between neighboring points. The lattice is not being proposed as a literal microscopic checkerboard underlying reality. It is a computational device. As the spacing between the lattice points is made smaller and the size of the simulated region is controlled carefully, physicists can work toward results that correspond to the continuous theory. This approach is known as lattice quantum chromodynamics. It turns an otherwise extraordinarily difficult strongly coupled field theory into a problem that can be attacked with powerful computers. That does not make the calculation easy. Far from it. The number of possible quantum field configurations is immense, and researchers must use sophisticated numerical techniques to sample the configurations that contribute most importantly to measurable quantities. The calculations can consume enormous amounts of computing power, but they allow physicists to explore precisely the regime where simple analytical approximations struggle. To study the proton, researchers begin with quantum chromodynamics itself. They specify the relevant quark masses and the parameters defining the strong interaction, then construct mathematical operators carrying the same quantum numbers as a proton. The computer does not contain a tiny picture of 3 colored balls and wait for them to arrange themselves correctly. Instead, it evaluates correlation functions involving the underlying quark and gluon fields. From the way these correlations behave across the lattice, physicists can extract the energy of the lowest lying state with the proton's quantum numbers. That energy corresponds to the proton mass. This is an extraordinary test. The calculation begins with very light up and down quark masses and massless gluons. Yet the resulting interacting quantum state emerges with a mass close to the proton measured in laboratories. The missing mass appears naturally from the dynamics. One of the landmark demonstrations came from the Budapest-Marseille-Wuppertal collaboration. Using lattice quantum chromodynamics, the collaboration calculated the masses of the proton, neutron and a range of other light hadrons directly from the underlying theory. The resulting hadron spectrum agreed impressively with experimental measurements. This matters because quantum chromodynamics was not merely being adjusted separately to make each particle come out correctly. The same fundamental theory was being used to generate an entire family of strongly interacting particles. Protons emerged at roughly the correct mass. Neutrons emerged at roughly the correct mass. Other hadrons appeared with the appropriate pattern of masses as well. It provided powerful numerical evidence that the observed hadron spectrum really can arise from quark and gluon dynamics. For the proton mass puzzle, that achievement is difficult to overstate. Physicists are not simply saying that gluons contain lots of energy, or that confinement probably makes the proton heavy. They can place quantum chromodynamics on a lattice, include the small fundamental masses of the light quarks, allow the strongly interacting fields to behave according to the theory, and recover a proton whose mass is hundreds of millions of electron volts larger than those light quark masses alone. The large mass scale emerges from the calculation. Modern lattice research can go further. Researchers use similar methods to study how quark energy, gluon energy, explicit quark mass terms and effects related to the trace of the energy momentum tensor contribute to the complete proton state. These calculations can test proposed mass decompositions and examine how different terms combine to reproduce the known total. They also reveal why simple percentage statements require care. The proton mass is an unambiguous measurable quantity, but individual contributions can depend on how the quantum field theory calculation is organized and renormalized. The computer does not reveal a collection of separate piles of mass hidden inside the proton. It reveals the behavior of one interacting quantum system. Perhaps the most remarkable result is how little heavy material needs to be inserted at the beginning. There is no constituent with a fundamental mass approaching 938 million electron volts waiting inside the input data. The up and down quarks remain fundamentally light. The gluons remain fundamentally massless. What changes is what happens when quantum chromodynamics brings those fields together in its strongly coupled regime. Confinement develops. Gluon fields become intensely active. Quarks become dynamically dressed. A characteristic strong interaction scale emerges, and the lowest energy state with the appropriate quantum numbers becomes a proton with nearly 1 billion electron volts of rest energy. In that sense, building a proton inside a computer provides one of the clearest answers to the original mystery. Most of its mass does not have to be inserted as the masses of its ingredients. It can be generated by solving the dynamics of the strong interaction itself. The proton is heavy because quantum chromodynamics makes it heavy. And modern computation allows physicists, remarkably, to watch that mass emerge from the theory in numbers. The proton's complicated interior was not discovered by simply looking at one. At the scale of a proton, ordinary microscopes are useless. Visible light has wavelengths far too large to resolve structures only around a femtometer across. To investigate something that's small, physicists need probes with much shorter wavelengths, which means using particles carrying enormous amounts of momentum. One of the most important techniques became deep inelastic electron scattering. The basic idea is surprisingly familiar. If you want to learn what is inside something, you can throw a probe at it and watch what comes back. Ernest Rutherford had used a similar principle when alpha particles revealed the existence of the atomic nucleus. Decades later, physicists pushed the same general strategy to much smaller scales by firing energetic electrons at protons. Electrons are particularly useful because they do not participate in the strong interaction. They interact electromagnetically, allowing them to probe the proton without themselves being strongly interacting composite particles. At relatively low energies, an electron can scatter from a proton in a way that reflects the proton as a whole. Increase the energy, however, and the electron begins to resolve finer internal structure. In deep inelastic scattering, the collision transfers enough energy and momentum that the proton is usually broken apart. What matters is the pattern in which the electrons scatter and how that pattern changes as the momentum transfer increases. During the 1960s, James Daniel Bjorken developed an important theoretical prediction concerning these high-energy interactions. He found that under certain conditions, quantities describing the scattering should display a behavior known as Bjorken scaling. Instead of depending strongly on every detail of the collision energy, the scattering could approximately organize itself around particular dimensionless combinations of the variables involved. That would be difficult to understand if the proton was simply a smooth, indivisible blob of matter. It made much more sense if energetic electrons were striking small, point-like constituents inside it. Then came the experiments. At the Stanford Linear Accelerator Center during the late 1960s, Jerome Isaac Friedman, Henry Way Kendall, Richard Edward Taylor and their colleagues fired high-energy electrons into proton targets and carefully measured how those electrons scattered. The results were striking. The electrons behaved as though they were much smaller, concentrated objects inside the proton. This had an important historical resemblance to Rutherford's earlier discovery of the nucleus. Just as unexpectedly large angle scattering had once revealed that positive atomic charge was concentrated in a tiny nucleus, high-energy electron scattering now suggested that the proton itself contained point-like constituents. These experiments became some of the strongest evidence for the emerging quark picture. Jerome Isaac Friedman, Henry Way Kendall, and Richard Edward Taylor later received the 1990 Nobel Prize in Physics for their pioneering investigations into the deep inelastic scattering of electrons from protons and bound neutrons. But the interpretation was still developing. Richard Phillips Feynman introduced an especially useful way of describing what the experiments seemed to reveal. He called the internal scattering objects partons. In Feynman's picture, a proton moving extremely quickly could be treated as though it contained point-like constituents, each carrying some fraction of the proton's total momentum. The word parton was deliberately somewhat neutral. At first, the experimental evidence revealed point-like components without requiring every detail of their deeper identity to be settled immediately. As quantum chromodynamics developed, the connection became clearer. The charged partons detected through electron scattering were associated primarily with quarks, but the proton's full partonic structure also included gluons and the sea of additional quark and antiquark contributions generated by the strong interaction. That richer picture became increasingly unavoidable as experiments grew more precise. The distributions of quarks inside the proton could not remain unchanged at every resolution. When the proton was examined more closely, quantum chromodynamics predicted that gluon radiation and quark-antiquark processes would alter the apparent distribution of partons. And that is exactly the sort of behaviour experimentalists found. Later measurements at the European Organisation for Nuclear Research extended knowledge of the proton and the strong interaction across new energy ranges. An especially detailed picture came from the Hadron Electron Ring Accelerator at Deutsches Elektronen Synchrotron in Hamburg. There, electrons or positrons were collided with energetic protons, allowing researchers to probe the proton across an enormous range of momentum fractions and distance scales. The resulting measurements revealed a proton whose internal structure depends strongly on how it is examined. At some momentum fractions, valence quarks remain prominent. At smaller momentum fractions, gluons and C-quarks become increasingly important. The gluon contribution is particularly significant. Although an electron does not couple directly to a gluon through electromagnetism, the effects of gluons can be inferred through the way quark distributions change with resolution and through other scattering processes predicted by quantum chromodynamics. Over time, this built an increasingly detailed picture of a proton filled with strongly interacting quark and gluon fields. Yet one important caution remains. Proton distributions describe how momentum is shared in a rapidly moving proton under particular probing conditions. They should not be interpreted as a photograph of a proton at rest containing a fixed number of little particles, each permanently occupying a known position. The Proton picture is enormously powerful, but it belongs to quantum field theory. The apparent number and distribution of partons change with the resolution scale. Probe more deeply, and more of the underlying quantum structure becomes relevant. This experimental evidence does not tell us that one particular gluon carries a certain fixed amount of the proton's mass, nor does it allow the proton to be divided into little containers labelled quark mass, gluon mass, and C-quark mass. What it does establish beyond reasonable doubt is the richness of the proton's internal dynamics. The proton is not three stationary valence quarks. It contains substantial gluon activity. It contains C-quark and anti-quark contributions. Its momentum is distributed among an evolving population of partons whose behavior follows the predictions of quantum chromodynamics, and this matters enormously for understanding its mass. The experiments revealed the ingredients and dynamics whose energy must be accounted for. They showed that the proton's apparently simple exterior hides an intensely active internal quantum world. From the outside, one proton looks much like another. But strike one hard enough with a sufficiently energetic electron, and the calm little particle opens into an entire landscape of quarks, antiquarks, and gluons. That landscape is not merely an interesting detail of proton structure. It is the experimentally revealed world from which most of the proton's mass ultimately emerges. A proton does not merely contain energy. That energy is arranged. It has a spatial structure, with different regions associated with different patterns of pressure, stress and force. And although those words sound surprisingly mechanical for something built from quantum fields, they provide another useful way of understanding just how energetic the proton really is. The natural starting point is the energy-momentum tensor. This mathematical object appears throughout modern field theory. It describes quantities including energy density, momentum flow, pressure and stress. Earlier it provided a way of thinking about the proton's total rest energy. But it can also be examined spatially, allowing physicists to ask how that energy and mechanical structure are distributed throughout the proton. This leads to quantities known as gravitational form factors. The name can be slightly misleading. Physicists are not firing tiny packets of gravity into protons and watching what happens. In fact, gravitational interactions at the scale of individual protons are far too weak for that to be a practical experimental technique. They are called gravitational form factors because the energy-momentum tensor is the quantity that would couple matter to gravity in a relativistic description. So by learning about the proton's energy-momentum tensor, physicists are indirectly studying the properties that would determine how its energy, momentum and internal stresses relate to gravity. These form factors contain information about the proton's internal mechanical structure, including distributions associated with pressure and shear forces. And remarkably, some of this information can be approached experimentally. One especially important process is deeply virtual Compton scattering. In this kind of experiment, a high-energy electron interacts with a proton by exchanging a highly virtual photon. The proton emits a real photon and remains intact, allowing researchers to extract information about the proton without simply smashing it completely apart. The measurements can be used to constrain quantities called generalized Parton distributions. Generalized Parton distributions extend the familiar idea of Parton distributions by containing information connected not only to the momentum carried by quarks and gluons, but also to aspects of their spatial structure. Through mathematical relations between these distributions and the energy-momentum tensor, experiments can therefore provide indirect information about the proton's mechanical properties. Jefferson Lab has used deeply virtual Compton scattering measurements in this broader effort to explore the proton's internal pressure and the strong interaction responsible for it. The resulting picture is extraordinary. Analyses of experimental data have suggested that the center of the proton contains an enormous outward pressure. Early extractions placed the central pressure on the order of 10 to the 35 pascals. That is an almost absurdly large number by everyday standards. The pressure inside the tires of a car is roughly a few 100,000 pascals. The pressure deep inside Earth reaches hundreds of billions of pascals. Even neutron stars involve pressures so extreme that ordinary intuition gives up fairly quickly. Yet the characteristic pressures associated with the proton can reach still more astonishing values because enormous energy densities are concentrated across distances of roughly a femtometer. The early experimental extraction indicated strong repulsive pressure near the proton's center together with binding pressure farther outward. Later lattice quantum chromodynamic calculations have independently studied both pressure and shear distributions within the proton. The important point, however, is not merely that the numbers are huge, the pressures balance. If the proton experienced only outward pressure, it would not remain a stable object. If everything were directed inward without a compensating structure, the picture would be equally incomplete. Instead, quantum chromodynamics produces a stable configuration in which different internal stresses balance one another. Outward repulsive behavior in one region is accompanied by inward binding effects elsewhere. The overall mechanical stability of the proton emerges from that balance. This does not mean there is a literal wall around the proton holding pressure inside. There is no microscopic metal shell surrounding three quarks, nor should we imagine a conventional gas pressing against the walls of a tiny container. Pressure in this context is a property derived from the spatial distribution of energy and stress in the quantum fields. The classical analogy is useful only up to a point. What really exists is an interacting state of quark and gluon fields whose energy-momentum tensor can be interpreted in terms of these mechanical quantities. The shear forces are part of this picture as well. Shear describes stresses that act in directions tangential to a surface rather than simply inward or outward. Together, pressure and shear provide a richer description of how the proton's internal quantum structure maintains mechanical stability. And once again, gluons are impossible to ignore. The gluonic sector contributes profoundly to the energy-momentum tensor and to the strongly interacting environment responsible for proton structure. Modern lattice calculations continue to investigate gravitational form factors and the separate quark and gluon contributions to the proton's mechanical properties. This also brings the trace anomaly back into view. The trace of the energy-momentum tensor is tied to the quantum breaking of classical scale symmetry. and therefore to the emergence of the characteristic mass scale of quantum chromodynamics. So the proton's mass, internal pressure, gluon dynamics, and quantum scale generation are not completely separate mysteries. They are different ways of examining the same strongly interacting quantum object. That does not mean pressure can simply be added up and called mass, nor does it mean the trace anomaly alone can be pointed to as a single substance responsible for everything. The relationships are subtler than that. But the mechanical picture offers another way to appreciate what the proton's mass really represents. A proton is not heavy because some invisible material has been packed inside it. Its mass reflects the total energy of a remarkably organized quantum state. Within a region only about a femtometer across, quark and gluon fields carry momentum, generate immense stresses, interact strongly, and settle into a stable configuration. From the outside, the proton appears almost impossibly simple. It has a definite charge, a definite spin, a definite mass, but inside that calm exterior is maintained by one of the most energetic and intricate balancing acts found anywhere in ordinary matter. The proton's mass is not an extra substance sitting inside that balancing act. It is one of the measurable consequences of the balancing act itself. There is a very simple thought experiment that reveals just how unusual the proton's mass really is. Imagine gradually turning down the fundamental masses of the up quark and down quark, not removing the strong interaction, not changing the gluon field, not dismantling quantum chromodynamics, just reducing the part of the light quark masses that comes from their interaction with the Higgs field. Keep turning those masses down until, in the idealized limit, the up quark and down quark become massless. It might seem obvious what should happen next. If the quarks inside the proton lose their fundamental masses, perhaps the proton should lose its mass as well. But that is not what quantum chromodynamics predicts. A substantial proton mass would remain. This idealized situation is known as the chiral limit. In that limit, the fundamental current masses of the light quarks are taken towards zero, and the light quark sector of quantum chromodynamics approaches a more symmetric form. Yet the strong interaction does not disappear. The gluons remain. Their self-interactions remain. Confinement remains part of the theory. The running of the strong coupling remains. Dimensional transmutation still generates a characteristic strong interaction scale, and the non-perturbative quantum dynamics that create hadrons are still present. So even when the explicit up quark and down quark masses are removed, quantum chromodynamics still contains the machinery required to generate massive composite states. The proton would therefore not simply collapse towards zero mass. Its precise mass would change, but most of its characteristic hadronic scale would survive. This is perhaps one of the clearest ways to see why the Higgs field is not the main source of the proton's mass. The Higgs mechanism gives the up quark and down quark their fundamental mass parameters. Those contributions are real. But if those parameters can be taken towards zero, while a heavy proton like hadronic state largely survives, then they cannot be responsible for most of the original proton mass. The dominant contribution has to come from somewhere else. That somewhere else is the strong interaction. Quantum chromodynamics generates energy through quark motion, gluon fields, confinement, dynamical dressing, and the emergence of its own characteristic scale. All of those features survive in important form even when the light current quark masses are removed. The proton therefore provides a striking example of dynamically generated mass. Its mass is not simply inherited from heavy ingredients. It emerges from the behavior of the interacting quantum system. There is, however, an important warning. None of this means that the real masses of the up and down quarks are unimportant. They matter greatly to the detailed world we actually inhabit. The up quark and down quark have slightly different masses, and that difference contributes, together with electromagnetic effects, to the subtle mass difference between the proton and neutron. The neutron is only slightly heavier than the proton. That small difference has enormous consequences. It affects which particles are stable, it influences nuclear reactions, it plays a role in the structure of atomic nuclei, and ultimately, it helps determine the kinds of matter that can exist for long periods of time. The strange quark mass also matters throughout the broader spectrum of strongly interacting particles. Change these fundamental quark masses, and the masses of hadrons shift. The properties of pions change. Nuclear physics changes. The detailed structure of ordinary matter changes with them. So the statement is not that Higgs-generated masses are irrelevant. The statement is much narrower and much more precise. They are not responsible for most of the proton's mass. The Higgs field is also essential for the mass of the electron. That matters enormously for atoms. Electron mass influences atomic size, energy levels, and the behavior of chemistry. A universe with drastically altered elementary particle masses could therefore have very different atoms, molecules, stars, and nuclear reactions, even if quantum chromodynamics still generated a large hadronic mass scale. So there is no need to choose between the Higgs mechanism and quantum chromodynamics, as though only one of them matters. They answer different questions. The Higgs mechanism helps explain why elementary quarks and charged leptons possess fundamental rest masses. Quantum chromodynamic dynamics explain why composite hadrons such as the proton acquire masses far larger than the bare masses of their light quark ingredients. The two mechanisms coexist. But for the particular question of where a proton gets most of its mass, one clearly dominates. Removing the light quark's Higgs-generated mass does not remove most of the proton. The proton remains a strongly interacting quantum object with a characteristic mass set largely by the scale generated inside quantum chromodynamics itself. The quarks would be fundamentally lighter. The hadronic state would still be heavy. And that contrast tells us almost everything we need to know. Most of the proton's mass was never sitting inside the bare up quark and down quark masses in the first place. It was emerging from the energetic quantum world those quarks inhabit. The Higgs field helps determine what the light quarks are. Quantum chromodynamics determines, to a remarkable extent, how heavy the proton built from them becomes. Most of the mass of a proton does not remain an isolated curiosity of particle physics. It becomes the mass of the ordinary world around us. Place protons back where they are usually found, inside atomic nuclei, and they sit alongside neutrons. Together, these two particles make up almost all of the mass of ordinary atoms. A neutron is closely related to a proton. Like the proton, it is a baryon built from 3 valence quarks. But instead of 2 up quarks and 1 down quark, a neutron has 1 up quark and 2 down quarks. That small change alters its electric charge. The proton is positively charged. The neutron is electrically neutral overall, yet their masses are remarkably similar. A neutron is only slightly heavier than a proton, even though their valence quark content is not identical. That similarity immediately tells us something important. Neither particle gets most of its mass from simply adding together the fundamental masses of its light quarks. If that were the dominant effect, changing the balance of up quarks and down quarks would produce a much more straightforward relationship between quark masses and the total masses of the proton and neutron. Instead, both particles receive the overwhelming majority of their mass from the same underlying source. The dynamics of quantum chromodynamics. The quarks inside them carry energy and momentum. The gluon fields carry energy and momentum. The strong interaction confines the entire system into a stable hadronic state. The characteristic scale generated by quantum chromodynamics determines most of the rest energy of both protons and neutrons. And once those particles gather inside atomic nuclei, that strong interaction-generated mass becomes the dominant contribution to the mass of ordinary matter. Electrons add something as well. An ordinary neutral atom contains one electron for every proton in its nucleus. Electrons are elementary particles, and their mass is connected directly to the Higgs field through the Higgs mechanism. So here the Higgs field really does provide the fundamental mass of the particle itself. But an electron is much lighter than a proton or neutron. Its rest energy is a little over 500,000 electron volts, compared with roughly 938 million electron volts for a proton. So an electron has less than 1,000th of the mass of a proton. In an ordinary atom, electrons are essential for chemistry, bonding and almost everything that determines how matter behaves on human scales. But they contribute only a small fraction of the atom's total mass. Most of the mass sits in the nucleus, and most of the nuclear mass comes from protons and neutrons. Even then, the total mass of a nucleus is not simply the masses of all its protons and neutrons added together. Nuclear binding changes the total. When protons and neutrons combine to form a bound nucleus, energy can be released. Because energy contributes to mass, the resulting nucleus generally has slightly less mass than the same protons and neutrons would have if they were separated and free. This difference is known as the nuclear mass defect. It is another example of the same broad principle that has been important throughout the proton story. The mass of a composite system depends on the total energy of that system. Binding energy matters. Internal motion matters. Field energy matters. The mass of the whole is not required to equal the simple sum of the rest masses of isolated ingredients. The effect of nuclear binding is significant in nuclear physics, but it is still smaller than the much larger quantum chromodynamic contribution already built into the masses of the individual protons and neutrons. So if you weigh an ordinary object, most of what the scales are responding to can ultimately be traced back to hadronic mass. That includes a table, a glass of water, a rock, a human body. The atoms in these objects may be arranged in wildly different molecules, but their nuclei are still built primarily from protons and neutrons, and the masses of those protons and neutrons are dominated by strong interaction energy. Lattice quantum chromodynamics has provided one of the strongest confirmations of this picture. By numerically calculating the behavior of quark and gluon fields from the underlying theory, physicists can reproduce the masses of light hadrons, including protons and neutrons, with impressive agreement with experiment. The result is remarkable because most of that mass is not inserted into the calculation through the fundamental masses of the light quarks. It emerges from the strong interaction itself. This means that much of the mass of ordinary visible matter is an emergent property of quantum field dynamics. But that statement has limits. It does not mean quantum chromodynamics explains all the mass and energy in the universe. Dark matter remains unidentified. Dark energy concerns the large-scale behavior of the universe and is not explained by proton structure. Stars also contain enormous amounts of energy in radiation and motion. Black holes can possess vast masses whose description belongs to gravity and general relativity, so the claim applies specifically to ordinary baryonic matter built from atoms. Within that domain, however, the conclusion is striking. Take the mass of a familiar object and trace it downward. From the object to its molecules. From molecules to atoms. From atoms to nuclei. From nuclei to protons and neutrons. From protons and neutrons to quarks and gluon fields. And eventually, most of the mass does not end at a collection of heavy elementary particles. It ends in energy. Energy associated with confined quarks. Energy carried by gluon fields. Energy produced by the strong interaction and organized into stable hadrons. The enormous scale difference makes this especially remarkable. The relevant quantum chromodynamic activity occurs within regions only around a femtometer across, yet the consequences are carried upward through every layer of ordinary matter. A phenomenon taking place inside objects far smaller than an atom becomes the weight of mountains, oceans, buildings, and living things. The proton, therefore, gives us a much deeper answer to the question of what ordinary mass really is. Its mass is not mostly a substance stored inside its quarks. It is the measurable rest energy of a strongly interacting quantum state. And because protons and neutrons make up most of the mass of atomic nuclei, that same quantum origin quietly becomes the mass of almost everything familiar around us. The proton gets most of its mass from the energy of the quark and gluon fields governed by quantum chromodynamics. And much of the ordinary matter we can see and touch carries that same origin with it. So where does a proton really get most of its mass from? Not from simply adding together the masses of the three valence quarks that define it. A proton is associated with two up quarks and one down quark. But the fundamental masses of those light quarks account for only a small fraction of the proton's total rest energy of roughly 938 million electron volts. That is the central surprise. The Higgs field does give the up quark and down quark their fundamental masses through their interactions with it. Those Higgs-generated mass terms are real and important. But they are far too small to explain why the complete proton is so much heavier. The missing mass is not hidden inside some undiscovered heavy constituent. It emerges from the proton as a complete quantum system. A proton is not three independent particles enclosed inside a tiny shell. It is an interacting state of quark fields, antiquark fields, and gluon fields. The two up quarks and one down quark describe its valence structure, helping determine its charge and identity. But alongside them is a sea of additional quark and antiquark contributions, together with an intensely active gluon field. All of these fields interact through quantum chromodynamics, the quantum field theory of the strong interaction. And this is where Albert Einstein's connection between mass and energy becomes essential. The invariant mass of a system is connected to its total energy in its own rest frame, so even when a proton as a whole is sitting still, its interior is anything but motionless. The quarks carry momentum, the gluon fields carry energy and momentum, the quarks interact with the gluons interact with one another. Energy is stored throughout the strongly interacting state, and because that energy belongs to the proton, it contributes to the mass of the proton. Quantum chromodynamics explains why this internal energy becomes so enormous. Quarks carry color charge, and gluons carry the strong interaction between them. But because gluons themselves carry color information, the gluon field interacts with itself. This produces the unusual non-linear behavior of the strong interaction. At very short distances and very high energies, the interaction becomes weaker through asymptotic freedom, discovered by David Gross, Frank Wilczek, and Hugh David Politzer. At the larger distances characteristic of a proton, the interaction becomes strong. quarks and gluons become confined inside color-neutral hadrons. They cannot simply drift apart as ordinary independent particles. The proton therefore exists in a regime where the interaction itself dominates the physics. That strong interaction also changes how light quarks behave. Through dynamical chiral symmetry breaking, the up and down quarks become dressed by their strongly interacting quantum environment. Their effective low-energy behavior reflects a much larger scale than their tiny fundamental current masses would suggest. But again, this does not mean the Higgs field secretly gives each quark hundreds of millions of electron volts of hidden mass. The larger scale is generated dynamically by quantum chromodynamics. The theory goes deeper still. If the fundamental masses of the light quarks are taken toward zero, quantum chromodynamics still produces a characteristic physical scale. The strong coupling runs with energy. Through dimensional transmutation, a theory beginning with a dimensionless coupling develops a characteristic energy scale. And because the classical scale symmetry of the idealized massless theory does not survive quantization unchanged, the quantum trace anomaly appears. That anomaly is closely connected to the emergence of the strong interaction scale and the existence of massive hadrons. These ideas are different pieces of the same underlying story. The proton does not become massive because one mechanism simply places mass inside it. Its mass emerges from the collective quantum dynamics of the strong interaction. Physicists can organize that total energy in several useful ways. Xiangdong developed an influential framework using the energy-momentum tensor to separate contributions associated with quark masses, quark energy, gluon energy, and the trace anomaly. Lattice quantum chromodynamic calculations have explored these contributions in detail, but the percentages should always be treated carefully. The proton's total mass is definite and measurable. The exact way that mass is divided into separate theoretical terms can depend on the renormalization scheme, the energy scale, and the particular decomposition being used. There is no universal collection of fixed slices physically sitting inside the proton. What is unambiguous is the dominant role of strong interaction dynamics. Experiments support this picture from another direction. Deep inelastic electron scattering at the Stanford Linear Accelerator Center during the late 1960s revealed point-like constituents inside the proton. The work of Jerome Isaac Friedman, Henry Way Kendall, and Richard Edward Taylor provided crucial experimental evidence for the quark structure of matter. Later experiments revealed an increasingly rich internal world of valence quarks, C-quarks, antiquarks and gluons. The proton seen at high resolution is not a quiet three-particle object. It is a complicated, energetic quantum state. And perhaps the strongest confirmation comes from computation. Using lattice quantum chromodynamics, physicists can begin with the underlying theory, including the small fundamental masses of the light quarks, and numerically recover the masses of protons, neutrons and other light hadrons. The proton scale emerges from the theory. It does not need to be inserted as the mass of some heavy hidden ingredient. That is the remarkable answer. A proton gets most of its mass from the energy of the strongly interacting quark and gluon fields that make the proton exist as a stable bound state in the first place. The Higgs field contributes through the fundamental masses of the light quarks, but quantum chromodynamics provides most of the proton's rest energy. And because protons and neutrons make up almost all of the mass of ordinary atomic nuclei, this same mechanism accounts for most of the mass of the familiar matter around us. The weight of a stone, a glass of water, a human body, or almost any ordinary object can ultimately be traced down to protons and neutrons. And inside those particles, most of that mass is not sitting in heavy elementary constituents. It is emerging from motion, fields, confinement, quantum interactions, and the characteristic scale generated by the strong force. So the simplest accurate answer is also one of the strangest. A proton gets most of its mass from energy, not energy added from outside. But the energy of the quantum fields whose restless, strongly interacting behavior makes a proton at all.